Thanks everyone for joining. I'll be giving a research update today on what I've been working on for mostly this summer, which is long-range precision satellite formation flight. To motivate this, space is becoming an increasingly more complex and cluttered domain. And so, especially in today's geopolitical climate, it's important to be able to classify any potential adversary agents. And sensing techniques such as, for example, X-ray can achieve this. For this, we can use two deputies that surround our uncooperative target, one being a sender of the X-ray signal, one being the receiver, and it essentially just X-rays the object to help us classify what it is made of and if it's a potential adversary agent. This obviously requires a very exact collinear formation of the three agents. This is also what motivated this proposal by Lincoln Lab that was brought to us a few months back with specific constraints to this problem. They set the constraint of achieving a 20+ kilometer baseline between the two deputies and a very precise collinearity deviation of no more than 10 centimeters, a collinearity deviation rate capped at 1 centimeter per an interval of 30 seconds, and also only a 1% baseline deviation. Very tight constraints, therefore, over very large baseline. This motivates a variety of problem statements because this is an end-to-end problem, starting with the formation design. And here I asked myself, what are the best formation designs for these large baseline inspection missions? And also, if we design those using our linear mapping between relative orbital elements and RTN, how does this extend to these large baselines when we actually run it with the nonlinear dynamics? And then, not to be understated, are also the navigation and control problems that can be asked here. So how can we achieve these really tight navigation and control accuracy constraints? Today, I'm not going to address navigation and control and focus on formation design, but I did want to mention these as they are very essential to this problem further down the road. To address the state of the art, several missions have pushed for very high relative position control accuracy, either in flight or in simulation. For example, Proba 3 or visors, pushing for a millimeter level relative position accuracy at formation baselines at up to 150 meters between the deputies. There's also a concept of MDOT that is an occulter observer geometry over 500 kilometers that try to achieve a relative position control accuracy of about 10 centimeter level. However, all of these missions have in common that they have two deputies collinear with an external fixed target, such as the sun or star. With this new problem, we have the to-be-observed target in the middle between the agents. And we're also pushing for a really high level of accuracy, precision at very large baselines. And this combination is exactly where the devil lies in the detail. So for today and what I've been up to over the past few weeks, the contributions that I've made were looking at different formation designs for achieving these goals. First one that I've just labeled formation design A here for ease of labeling follows closely the visors-based approach. First of all, let me say we describe each of our deputies with its own set of relative orbital elements, say delta alpha, and to meet the collinearity constraints in the linear frame, we enforce the anti-symmetry of these relative orbital elements. So one is the negative of the other. Then we start by setting delta A to 0 to avoid circular along track drift. And we also choose the along track separation to be 0 for both deputies. Then, as you're all probably very familiar with, we write the relative eccentricity and inclination in its polar form and enforce EI vector separation for passive safety. So we demand that both relative eccentricity and inclination are in phase. So far, so good. this is where it gets a little bit more interesting to fix also the semi-axis length of the ellipse that this relative motion draws in the Rn plane, as seen on the right here. We parameterize it with an angle beta that is essentially the ratio of how far does the ellipse in the Rn plane extend in the radial direction versus in the normal direction. So this is an example plot for beta 30 degrees, which means that we have this extension, the extension is larger in the radial direction than in the normal direction. And then how do we choose S? So the total separation between the two deputies is characterized by this formula, square root, the large square root formula, and it is an oscillating function. It is minimal when we set theta, which is just u plus phi, to 0, and then it still yields 2s cosine beta. Now remember that our initial constraint was that our baseline was 20 plus kilometers. So we set our baseline at this minimum at theta equals 0 to be exactly 10 kilometers per deputy, so a total of 20 kilometers. Yeah, and our observation period is then consequently also at theta equals 0. This also ensures that since we choose the baseline such that as the observation period, it's a local minimum of the total separation, the total separation will change with the slowest rate possible. And so we can hopefully achieve the longest time that we stay within bounds of our baseline requirement. What is still open here to determine the final ROEs are the values for phi and beta. In the visor's design, beta is defined by the angle to the external object that is projected into the orbital plane. We don't have this constraint here. One could go ahead and do some error budgeting and put some lower or upper bound on beta this way. And phi is also still to be chosen. So there's some multi-parameter trade space here. Oops. So this is just a summary of the final ROEs that I'm receiving with the parameters I've just outlined. And I've plotted an example demonstration of the relative motion in the Rn plane and the RT plane for a selection of beta equals 30 degrees, phi equals 90 degrees. We can see that the deputies are opposite of each other with respect to the chief, which is the black dot in the middle in this linear setting, which is what we wanted to achieve by design. Now, to evaluate how good this formation design and also the further formation designs will be, I'm outlining the metrics here. The collinearity deviation is defined as the perpendicular offset that one deputy has to the extended line between the other deputy and the chief, as you can see in this visualization on the right. I'm saying this because you could also go ahead and define the collinearity deviation as how far does the chief deviate from the line between the two deputies, but that is different. So this is the deviation that is proposed as a metric by the original project proposal. And to determine the collinearity deviation rate, I use the finite difference method of the adjacent absolute positions of the deputies. And then I also looked at delta V cost to counteract any secular J2 induced drifts of the relative eccentricity. And you're probably more than familiar with this, yet I still wanted to bring it up here, assuming tangential burns because they couple the most efficiently to our delta R, T, and N. Delta V is precisely given by this formula, and the change of the relative eccentricity over a certain amount of time is proportional to its original relative eccentricity and then how far the eccentricity phase has shifted due to the J2 effect. So what this design reveals, this is again for beta to 30 degrees and phi equals 90 degrees. The collinearity constraints here are very sparsely met. So you can see that right in the middle at 180 degrees is when we meet the collinearity deviation the collinear deviation requirement the best. However, that is when we have a high spike in the deviation rate. And taking all of these together, we only meet all the constraints in the same interval for 0.83 seconds. The trend here is that with lower beta, we get a larger window for which the constraints are all met. Yet you can also play around with phi. And this is a trade space I still want to explore further, but it does not seem like there's a phenomenal constellation that solves all our problems at once. Another downside of this is that we have huge relative eccentricities, and that's why we get a very large delta V of 0.074 meter per second per orbit for each deputy, and then that scales up to weekly budget of 15.67 meter per second per weekend per deputy. So overall, we can get the feeling that maybe this is not the best way to exploit our natural motion to make this large baseline formation design possible. So there's another approach, which I call formation design B. And this one exploits the large baseline along the along track separation. So imagine we have our chief sitting in the RTN frame, and then we want to place our deputies at 10 kilometers plus and minus away. Then the problem is that at these 10 kilometers, we actually have to start thinking about taking the curvature of the orbit into account. And in this case, for value for A of 7,100 kilometers, so in Leo, we get this value to be of around 7 meters. So one proposed formation design to counteract this, it's actually based on the work of a previous undergrad student, Isabel Portios. I hope I'm saying her name right. So what was suggested there is to introduce an anti-parallel relative eccentricity for each deputy of exactly that offset of 7 meters to compensate for the orbit curvature. So in a very exaggerated way, you can imagine the eccentricity kind of introducing a lateral shift, if you will, to the orbit. And if you zoom in, we want to, sorry, try to,
I said radial.
Oh, okay, yeah, thank you. Did I say something different? It doesn't matter.
Lateral.
Oh, sorry. Yeah, so if we zoom in, we hope to achieve collinearity like this, with the two deputies, one being ahead in delta lambda, one being behind, one a little bit further out, one a little bit further in. And this is what that suggested design would then look like in ROEs. We see that by design, there's this collinearity between the deputies and the chief because we have the counter rotating relative motions on the ellipses. However, I personally, I don't think that it actually works if we extend it to the nonlinear domain when we have to take into account the 10-kilometer baselines. So this is trying to illustrate this. Even if we introduce these two counteracting ellipsoidal motions and we have both of them at their most exaggerated point in the radial direction, as you can see here, there's not a point where the connecting line between the deputies will actually be collinear. This is because we have a symmetric curvature of the orbit, but we're trying to counteract it with an anti-symmetric design. So I think unfortunately this doesn't work the way it was so beautifully intended in the linear case, but not all hope is lost because a very similar idea is to just have both deputies with an eccentricity in the same direction. That will not give us collinearity all the way around the whole orbit. It'll only give it at this instant, but we can still hope to exploit this and have a large enough window where we can make measurements in a collinear setting. So this is what that would look like with respect to, in the same plot visualization as the one I've previously shown. So for this, the orbital elements are as follows. I've highlighted that for both deputies, the eccentricity will have the same sign, and this is what its motion looks like, again, in the Rn plane and RT plane. Also, in a conceptual plot at the bottom, you can see that now the deputies are co-rotating in their relative motions at those plus and minus 10 kilometers. And to evaluate this design, as you can probably already tell by this conceptual plot, since the two deputies are co-rotating, the baseline is kept up very nicely. So we only have centimeter deviations from the baseline. Now, what's more interesting is the collinearity deviation, but as we can see in the uppermost plot, the orange curve, it dips down to our 10 centimeter requirement. And analyzing, zooming in on this further, you can see that the collinearity conditions are actually met together for 225 seconds. So that's like 3.75 minutes. So we actually do get a window where all the constraints are satisfied at the same time. And assuming that our sensing interval is about 30 seconds, this would give us a valid window to perform our sensing experiment once per orbit. Another huge advantage is that our eccentricities are now much smaller, so our delta V won't explode as much, and we actually get 59.9 micrometer per second per orbit per deputy delta V, which scales up to then 6.1 millimeter per second per week per deputy. Okay, so to summarize, this problem statement of having the very large baseline with very tight precision constraints poses unique challenges. I've compared essentially two concepts of formation designs. So one being based on visors. And there we noticed that we have very short periods of meeting all collinearity constraints at the same time, but because we introduce very large relative eccentricities, we have a high delta V. And there's a multi-parameter design space between the two values that were still left open by this design that I would like to explore further. We've explored an along track design with an antiparallel configuration of relative eccentricities for the deputies and found that that does not extend to the nonlinear case as we hoped. However, if we design an along track separated design with the same sign relative eccentricity for the deputies, then we have a few minutes where we meet our requirements every orbit, and it also has a more reasonable delta V. So other considerations that I've not made here are, for example, the oscillating effect of J2-induced drift. So far, we've only compared the mean, and that could definitely pose an issue to our very precise collinearity constraints. I've also not considered so far the drift of the relative inclination in the first design where it would apply. And of course, drag, since we're here in Leo. If the nominal formation design exploiting the natural motions of the dynamics does not turn out to be feasible, then could also look towards actively controlled formations. And at the very, like as a stretch goal in the future, finding the right navigation solutions and control solutions to achieve this precision is still a very large topic to be explored at the horizon. Yeah, with that, I would like to conclude. Thank you.